Hello, hello. We just finished talking big picture about at least our textbook's approach to kind of building a sort of slash quotation mark optimal regression model. We talked about sort of these 5 steps to greatness and kind of talked through them theoretically. Now we're going to kind of talk through them in the context of an example. Now, of all the examples out there, right, all the thousands upon thousands of data sets that we might have to kind of illustrate the topics that we've been talking about. Um, I don't know, what data set do you think would be like a good one to use? Any ideas? I don't know, maybe like a data set on fish. It's maybe one possibility. Maybe there's some data set on giraffes. That would be kind of cool. Um, Maybe like a data set on little koala bears. Oh, they're so cute. I love those. Oh, actually, bears is not a half bad idea. Hey, actually, why don't we have this data set, don't we? Have like 99 beloved bears. Why don't we actually take that data set, the data set that we've been working with for the last, I don't even know how many weeks, and let's finally put that sucker to rest, right? Let's actually take that data set that we've been working with time and time and time again, and let's use this approach to finally and conclusively answer what is the best bear model. Yeah, buckle up, Buttercup. Here we go. So, let's actually start with a somewhat restricted situation. Right, I know there are more variables than just chest length and gender, age, for example, neck girth, for example, in our bears data set. However, I'm going to focus on just these 3 because it's our first example. I want to keep things somewhat pedagogically simple. That said, adding the other variables wouldn't really be that big a deal. And you'll get kind of gradually larger and larger and larger examples as you work through labs and homeworks. And eventually, right, kind of the big one for you is going to be your impending take-home exam. So if we want to focus on just our variables of chest and length and gender, what is our maximum model? What is our K? How many variables are there in our largest possible model? It's not 3, right? It's not 3. Because we have to consider our pairwise interactions, we have to consider our second order polynomial terms. So what is it? Give you a second to kind of think about it. It might be tempting to say 9. It's not 9, agreed? It's not 9. I think it's going to end up being 8. So first off, how many pairwise interactions? Well, we have 3 variables, so if we think about it, any pairwise interaction essentially excludes a variable, right? So I could look at the pairwise interaction between chest and length, and that's essentially just saying exclude gender. And there's sort of 3 variables that could be excluded, so right, mathematically that implies there's 3 pairwise interactions. Not that hard to enumerate them. Chest and length, chest and gender, length and gender. Those are the only ones there are. So 3 pairwise interactions. It might be tempting to say 3 second order polynomial terms, but let's think about that. The idea of like the chest squared makes sense, length squared makes sense. But does the idea of gender squared make sense? It doesn't, right? I mean, what does male squared mean? What does female squared mean? Generally, we don't square categorical variables. Gender is an example of a categorical variable. So we have only 2 second order polynomial terms. So our total number of variables, our K, is going to be the 3 original variables plus the 3 pairwise interactions plus the 2 quadratic terms. Now you might say like, whoa, hold on there. What about the cubic terms? And that's a great question. Now, in our polynomial regression slides, remember you should have done those first. As well as some previous lab work, we know that the cubic term just doesn't seem justified. We know the cubic term doesn't seem justified. Right, and by lab work, do you remember in the partial f-test lecture? It always seems to go back to the partial f-test lecture. In the partial f-test lecture, we did an example of a chunk-wise f-test that tested for whether or not we needed some polynomial terms. So in that example, as well as our polynomial lecture slides, we saw the cubic term, at least for length, wasn't justified. And because of that, hey, I said let's not rehash old issues. Let's not worry about it. That said, in the absence of such knowledge, it certainly would not be unreasonable to put the length squared and the chest squared in there as well. So it's not a bad idea. I excluded them in this case because we've kind of already looked at them. Now, I again have to create all these additional terms. I could do that in a data step. So, right, I got my 3 interaction terms. I use inter LC as the interaction between length and chest, inter LG, interaction between length and gender, inter CG, interaction between chest and gender. I make length squared. We already talked about how gender squared doesn't make sense, and then chest squared. And so let's start them off. I'm actually going to walk through. We talked about 4 different approaches to model building. You remember what the 4 are? Go ahead and say it. Let's count them on our fingers. Okay, number 1 is correct. Number 2 is correct. Number 3 is correct. And number 4 is absolutely right. 4 out of 4. There's the all possible model approach. That's what we're going to talk about right now. There's the forwards approach, the backwards approach, the stepwise approach. So I'm going to do all 4 of them. I'm going to illustrate all 4 in terms of their data set. So we'll start with the all possible models. So I can do proc reg. I can do the model statement. Weight equals. I put all 8 variables into the right-hand side of my equation. And then we've seen this in maybe an earlier lab, but there's this process where we do selection equals. And we could put actually all 3 of those metrics that we talked about last PowerPoint. You could put R squared in there, CP in there, and MSE in there. And let's see what that looks like. Now remember, right, this is the approach that we talked about in the last set of PowerPoints. What are we basically doing? So these are technically ordered by R squared, but one thing we'll see is that ordering it by R squared is the same as ordering it by CP and same as ordering it by MSE. That is, they'll all kind of follow the same ordering. So what we're going to basically do is we're going to move from a 1 variable model to a 2 variable model to a 3 variable model. Right? That's technically our P, that very leftmost column, the 1 and the 2 and the 3, that's the P column. We're going to compare that to the mallow CP column. And we're going to look for when mallow CP is less than P. So what about the 1 variable model? In the 1 variable model, we have a P of 1. Our smallest mallow CP is 39.3. So in this example, the CP is still larger than P, so we keep going. What about the 2 variable model? The 2 variable model, now we have a P of 2. Our mallow CP, the smallest one, is 16.4. 16.4 is still larger than 2, so we got to keep going. So we go to 3. Now we have a P of 3. And of course, we don't have the screenshot of what comes after. This is just a truncated screenshot, but that first one, that first mallow CP is always the smallest. So the smallest mallow CP is 2.1. That is less than our P. That is less than 3. So we stop. The optimal number of variables out of our total possible number of variables out of our 7 variables. Out of our 7 variables, 3 seems to be the optimal number. Now, what is the best 3 variable model? That's going to be the one with the highest R squared. Again, our thing is already sorted by R squared, so that even though we're only seeing one of the 3 variable models, the one that we're seeing is going to be our optimal one. Actually, not that hard, right? So it's basically saying out of all the 2 to the power 7, 2 to the power 7 minus 1 models that we need to consider, the one that is the best one is going to be the one that includes chest and length and chest squared. Oh, actually, there's some more of the 3 variable ones, but if you look, they all have smaller, or yeah, they all have smaller R squareds and larger CPs. So there's a summary of the conclusion we just stated. The optimal model has 3 variables. Those variables are chest, length, chest squared. All right, and 1 out of 4 model building approaches done. Check. All right, so now forward selection. So to do forward selection, we again, proc reg, our usual model statement. We use that selection thing. We do selection equals forward. Now, we can couple the selection equals forward command with what's referred to as an SL entry command. Remember, I said in the previous slide that we have to specify a significance level. This automated process is going to make decisions based off p-values, and the computer needs to actually know what alpha we want to use. The fact that it's not 0.05 might be like a little bit disconcerting to us, a little disorienting to us. It turns out that for automated processes, it tends not to be 0.05. That is, programs tend to use more liberal alpha levels. In fact, I put a little snippet at the bottom there that's pasted directly from SAS help. We could see the default. So, I mean, there is a default. So I actually don't have to put the SL entry. If I didn't put SL entry, SAS would just use its default alpha level, which is actually 0.50. It's not a typo. It's 0.50, not 0.05. So that's even like more liberal than the 0.3 there. Now my 0.3 is somewhat arbitrary. I picked it for like for illustration purposes, for pedagogical purposes. In practice, I would maybe just say use the SAS default, to be honest, but I did want to show us that that default is something that we can change. So let's go ahead and take a look at what happens. So SAS kind of starts walking us through this process. It looks at all of our 7 variables and says, of these 7 variables, which one is the most highly correlated with a bear's weight? Turns out the answer to that question is chest squared. So it adds chest squared to our model. Then it keeps going. It says, okay, of all the variables, all the remaining variables, which ones are have the highest correlation with the bear's weight above and beyond what's being provided by chest? Turns out that's length squared. So in our second step, we add the variable length squared. Then in step 3, it says, okay, of all the remaining variables, which one adds the most? And that turns out to be chest. Notice if I look over, I look at the p-values for these things. All those p-values are less than 0.0001. So these are actually all, even though we were technically using a somewhat liberal alpha level of 0.30, everything that's been added is highly significant by usual standards. And then SAS says no other variables meet the 0.30 criteria. That is, if I were to add any other variable, its p-value would be 0.30 or larger. And so it stops. And so this basically says the forward process determined that our optimal model is chest squared, length squared, and chest. That's different than the all possible model approach. So that is showing us different approaches can lead to different models. Something that we'll have to reconcile in a few slides. So according to the forward approach, The optimal model has 3 variables. Those variables are chest, chest squared, and length squared. So far, so good? So man, look at us go. All possible models, check. Forward approach, check. Backwards, here we come. So backwards elimination, right? Same idea, right? We got a model statement, we got proc reg, we got selection. So instead of selection equals forward, we're going to do selection equals backward. Instead of an SL entry, we have an SL stay. So, right, instead of a significance level that needs to be met to enter a model, we have a significance level that needs to be met to stay in our model. Again, I pasted the thing. SAS default for this actually is like a little bit closer to what we're used to. The SL stay is 0.10, the default, but as I've illustrated, we could override that default. Now let's go ahead and look at what this looks like. So again, notice SAS starts with, this is the backwards approach. It starts with the largest possible model. That's got all seven variables in it. Now look at the p-values for those variables. Which variable is going to be removed first? Exactly. The variable that's going to get removed first is gender. Gender has the largest p-value, and it's above that threshold of 0.20. So we pull out gender, and we rerun our model. We can actually see at the very bottom of this screen, right? It says variable gender removed. And so now this is the 6 variable model. Oh no, I'm sorry. I kept saying 7. That's actually, we started with 8. So now this should be a 7 variable model. My bad. Now look at that. Which variable is going to be removed next? Exactly, it's going to be length squared. Length squared has that 0.3850. Right, so I remove length squared. And now I look at my remaining 6 variable model. I look at all the remaining variables. Looks like there's the interaction between length and chest now has the largest p-value, so that's what I'm going to remove next. And you get the idea, I hope. I think I cut out a screen or two, so it's kind of like a ... there. But SAS kept removing variables until eventually the only remaining variables were chest and length and chest squared. And all 3 of those variables we can see are actually highly significant. SAS then summarizes the process and tells us first it removed gender, then it removed length squared, and then it essentially removed all of those interaction terms. So, as we're going to see in the next slide, as we're going to reiterate in the next slide, our optimal model as determined by a backwards approach is chest, length, chest squared. There we go. Our optimal model has 3 variables, chest, length, chest squared. All right, backwards approach. Check. Dear me. My apologies. So stepwise approach, right? So here we do a model statement. Instead of selection equals forward, we do selection equals stepwise. Now remember, the stepwise process, it's mostly like the forward process. It's adding variables one at a time, but at every step, it reevaluates the variables in our model. And if their p-value has at some point become too large, it removes them. So it adds variables and removes variables. So it needs an SL entry and an SL stay. It has the flexibility to use different alphas for both of those 2 decisions. And so in this particular example, it actually ends up not being any different than our forward approach. So we run the stepwise process, and we get a model of chest, length squared, chest squared. All of those remain, so they were significant when they were added to the model. They're all still significant after other variables have been added. And so for this particular data set, stepwise and forward don't give any different results. In general, they can. And of course, in general, stepwise is better. So, I mean, in a lot of ways, stepwise is uniformly better than forward. It's essentially forward with this like extra step that, again, I guess is technically an extra amount of computation. But in this day and age, that extra amount of computation is just not a big deal. So why not do it? So by the stepwise approach, the optimal model has 3 variables. Those 3 variables are chest and length and chest squared. All right, so we did 4 approaches. 2 of those approaches picked chest, length, chest squared. 2 of those approaches picked chest squared, length squared, and chest. So we have to pick between those 2. Oh, I'm sorry. My slide says 3 of the approaches pick chest length and chest square. That's not true, right? That's a typo on my part. We 2 approaches picked one, 2 approaches picked the other. Now, I would steer clear of the chest squared, length squared. Why? A couple reasons, right? The length squared term, well, we have length squared but not length, right? And in our polynomial discussion, we said that if you have a squared term, you should have the base term. But we've seen if we have length, we don't need length squared. And so, right, that model becomes a little unattractive because of that property. We also saw, right, interestingly, even though the forward approach kind of like picked length squared as like the starting variable of all the variables, all our 8 variables, it picked length squared as the best one, right, to start with. Interestingly, when we looked at or evaluated the backwards approach, length squared was one of the first variables to go. I think it was technically the second variable. That is, even though length squared, I guess, is better than all others, it's also like the most unneeded in the presence of all the other variables. That is, it becomes redundant with other variables in the model. And so, with all that reasoning in mind, the final model that I would pick based off these 4 approaches would be chest, length, and chest squared. Now again, in practice, I would encourage you to do all 4 of these approaches. See where they agree, see where they disagree, and then use your critical thinking to try to figure out which of those 4, or maybe even some blend of the 4, is the best model. It's what I would hope you might do in a homework, in a lab, in a take-home test. Now, again, you get out and practice, the reality might be you don't have the time to do all that. I get it. But in our class, I do expect you to make the time. And by doing so, you're going to get practice with all 4 of these approaches. Now, I mentioned that we want to be careful using automated model building processes. Why? Because automated model building processes will sometimes do silly things. For example, include a higher order polynomial term without the lower order polynomial terms. And we just saw an example of that, didn't we? We had length squared but no length. There actually is a way to kind of fix this problem. We could fix this problem using the include statement. So this is just kind of showing you a little bit of extra bells and whistles in procreg. So here, the include option, it actually takes a number. And what that number is basically saying is it's saying include the first 3 variables, right? So again, that means that the order I write my variables in the model statement matters. It's saying take a look at all the variables on the right-hand side of your equation and keep the first 3 in your model no matter what. So that's what? That's basically forcing those variables to be in our model. It's forcing the lower order terms to stay in there, and then just basically seeing what higher order terms, if any, should be added. So let's see what the results look like. All right, so it starts with the variables we forced it to start with, chest length and gender, and then says, okay, of all the 5 remaining variables, the one that adds the most is chest squared, so it adds that, and we can see that p-value is less than 0.0001. And then it stops. It says no other variables are significant by the criteria we specified. So the only thing that gets added is chest squared. So now it gave us a model that has some polynomial terms as well as lower order terms. Now that said, right, again, just as this is like a preliminary step, I then might say, okay, even though I wanted to force gender in there just in case like maybe there was an interaction term that included gender, it turns out I can see that gender is not significant by the usual 0.05 criteria. I could see gender as a p-value of 0.3294. So I might take this model that the automated process gave me. I might refine it further by removing gender, and in which case we're now back to the model we had already decided upon: chest length, chest squared. Yeah, all right. So technically it gave us a model chest, gender, length because we forced those 3 variables in there. It added chest squared. So technically the automated process gave us a 4 variable model. I would suggest that we should then go ahead and remove gender, which of course just takes us back to the model we had already decided on. So again, just to reiterate, right, I picked certain SL entry and SL stay significance levels to illustrate certain pedagogical points. In practice, I've looked around. I can't really find a clear-cut rule. So I would suggest using the SAS defaults unless you have a convincing reason to do anything different. And then kind of from that, kind of follow up and only keep those things in our sort of final model based on that traditional 0.05, and then maybe some combination of scientific expertise and statistical reasoning kind of for our final model. So for the automated process, use those liberal ones. But at the end of the day, for the final model, I would usually not have anything in my model that doesn't have a p-value less than the usual 0.05, unless I had some convincing reason to do otherwise. Okay. All right. And I apologize for this. I'm going to add one last little thing. And I should have said this earlier in the lecture. I just forgot, and it's challenging to rewind these narrations. So I'm just going to give it to you at the end of this lecture. Remember we decided our maximum model would have a K of 8. I'm sure you remember that. And I talked about like the idea of cubic terms. We probably could have added the cubic terms. Actually, I guess we could have. It wouldn't have been that big a deal. But I do want us to also keep in mind, remember we talked about constraints on the number of variables we can put in our model? So remember our sample size is 99. So, and we said we want usually between 5 and 10 observations for every variable in our model. So in that sense, using 8 variables is really nice, right? So if you do 99 divided by 8, I don't have a calculator handy, but that's more than 10, right? So we have more than 10 observations for every variable. So that we're really good in terms of our constraints. I didn't illustrate that as clearly as I could have, but every time we pick our K, we should always take a minute to compare that K to our sample size and make sure that it's somewhere within that 5 to 10 variable, 5 to 10 observations per variable range. In our case, the 8 is actually better than the recommended 10 observations per variable, so we're in good shape. All right, so that wraps up our illustration of model building. The last thing that we have, remember, there's still this fifth step, this enigmatic fifth step. We talked about we evaluate the reliability of our model. So that's the last thing we need to do. And then that'll wrap up this week's lecture on polynomials and model building.